Hi folks, welcome to the Key Concepts Review for Chapter 5 of Math 521B, Pre-Calculus 11. Here we're looking at radicals, specifically simplifying, multiplying, and dividing radicals. Standard disclaimers apply, and as always you can check the video description below for a link to the downloadable notes so that you can do the presentation along with me if you like. So we'll start off with simplifying radicals, which you did in grade 10. Radicals are roots, like square roots, cube roots, etc. You need to know the first 20 perfect squares and the first 10 perfect cubes. And that was true in grade 10 as well. So you need to know that the perfect squares are 1, 4, 9, 16, 25, and so on. The cubes are 1, 8, 27, 64, and so on. From grade 10, we could have been asked to convert to a mixed radical form for root 75. And the way that we do it is we factor 75 into two parts, into a rootable part and to what I call leftovers. So you could split 75 apart as 15 and 5, but neither of those have a square root. If instead you split it apart as root 25 and root 3, then root 25 actually does have a square root, and we can evaluate it. So we've got it split apart. Now that rootable part, we'll actually figure out what it is. Square root of 25 is 5. We get 5 root 3. Now I wonder if that's true. I wonder if root 75 really is 5 root 3. Let's find out. On the calculator, we could ask it to do root 75 gives us a decimal approximation of 8.66. If I tell my calculator 5 root 3, it's going to give us, amazingly, 8.66. They must be equivalent. So you can always check your simplification that way. Does it give you the same value in both forms? Let's do one with the cube root. I've got the cube root of 250 here. I need to split it apart in a rootable. So this time it'll be a cube root and leftovers. Now my perfect cubes are going to be important here. They're 1, 8, 27, 64, 125, and up from there, 216. 216 is going to be too big. But 125 is a number with a cube root, and I can split 250 into it. What are my leftovers? Well, 250 is 125 times 2. And now I just evaluate that. Cube root of 125 is 5 times the cube root of 2. If I go in my calculator, those are going to be the same value, cube root of 250 and 5 cube root of 2. We can also go the other way. If we want to go to an entire radical, I need to take that rootable part and rewrite it as a square root. So 3 is the square root of something. And then I had that root 7. 3 is the square root of 9. So I have root 9 times root 7, or as an entire radical, root 63. Again, if I want to check it, 3 root 7 is 7.94, and the square root of 63, you already know it's just below 8. Yep, same thing. Okay, over here, we'd have to do the same thing, but with cube roots. So 4 is the cube root of something, and we also have a cube root of 2 we're multiplying by. 4 is the cube root of 64. Again, you need to know your perfect cubes. So this whole thing could be rewritten as cube root 128. I'm just multiplying what's under the radical signs. When converting to a mixed radical using variables, the same technique applies of splitting apart into rootables and leftovers. But you need to be careful because since a variable can take various values, you need to make sure you're not going to take the even root of a negative. In this example right here, the square root of 45 c squared times d cubed. 45 has a square root. It may not be a pretty one. C squared, you could put anything in for c. Even if you put negative 2 in, no problem. You still have a positive underneath that root sign. D cubed, you cannot put in negative numbers for d because that would cause the whole thing to be negative and there's no square root. So this has the restriction d is greater than or equal to 0. Another nitpicky thing we need to notice is about absolute values. The square root of 3 squared would be the square root of 9, or 3. The square root of negative 3 squared would also be the square root of 9, or 3. So notice square rooting a square, makes it positive. And there's a symbol for that called absolute value. Turns everything positive. So we say that the square root of x squared would not be x. It would be the absolute value of x. Be aware of the potential for needing absolute values when taking the even root of an even power. So we'll look at a few examples that involve that. State the restrictions and simplify. So first of all, in this one, I can put anything in for c. That's no problem, because even a negative number will get squared, and it'll be fine. I cannot put in negative numbers for d, because that would cause my whole thing to be negative. So the restriction is d is greater than or equal to 0. Now let's split it apart into rootables and leftovers. What can be square rooted? Well, from 45, you could split it apart into 9. C squared can be rooted. D cubed can't be, but you can take out part of it. D squared could be square rooted. And then what would that leave us? Leftovers would be 9 times 5 is 45. We dealt with all the c's, and we're left with one of these d's. Okay, let's square root. Square root of 9 is 3. Square root of c squared is absolute value of c. Square root of d squared is absolute value of d. And this is going to be root 5d. Now that's true, but one of these statements is redundant. You don't need to say the absolute value of d because we have the restriction d is greater than or equal to 0. So there's nothing wrong with it, but it's not required. There we go. There's the simplification if you put it in simplified form with the restriction. Let's try the same thing. We want to split this one up here into rootables and leftovers. Okay, and let's check out the restrictions. Can I put a negative number in for x? No, that would make the whole thing negative. Can I put a negative number in for y? Yes, it's fine. It gets squared. That turns it positive. Can I put a negative number in for z? No, that would make the whole thing negative. So we'll say z is greater than or equal to 0. There are our restrictions. Now let's split apart. 72 could be split apart into 36 and 2. And you should take the biggest rootable you possibly can. X cubed can be split apart into x squared and x. You can take the square root of x squared. You can take the square root of all of y to the 4th. And you can take the square root of z to the 4th. And that leaves us with a leftover of z. You can take the square root of any power, or any even power, rather. You can take SQRT of even powers. Okay, now let's do our square rooting. So square root of 36 is 6. Square root of x squared is absolute value of x. Square root of y to the 4th would be absolute value of y all squared. Square root of z to the 4th would be absolute value of z all squared. And leaves us with 2 root 2xz. And then let's look at our restrictions. Is there anything here that's redundant? Well, x had to be positive anyways, or 0, so it doesn't need an absolute value sign. Absolute value of y all squared is going to be positive no matter what. So that absolute value sign's not really doing anything. So we could simplify it to y squared. And z had to be greater than 0, so we really don't need absolute values for z. Root 2xz, x is greater than or equal to 0. Z is greater than or equal to 0. Let's try another one. We've got 4th root of c to the 9. So over here, it's safe to say c has to be greater than or equal to 0. If you put a negative in here, then you try and take the fourth root of a negative. You can't take the even root of a negative. How are we going to split this apart? Well, c to the 4 is going to have a fourth root, and any multiple of a power of 4 is going to have a fourth root. So I can split this apart as c to the 8, and that leaves me with the fourth root of c. The fourth root of c to the 8th, all we do is we divide in this direction. Okay, so we'll have 8 divided by 4. That's going to give us our new power on c. C squared, and we also have fourth root of c. C is greater than or equal to 0. Last one. We want to split this apart into rootables and leftovers. So it's a cube root. I've got a 54. What's a factor of 54 that's got a cube root? There's 27. Okay, I've got an x to the 6. Does that have a cube root? Yes, x to the 6 is just x squared cubed. So that's not part of the leftover scene. In the leftover scene, we have a 2, because 27 times 2 makes 54. Now let's check out the y's. We could take the cube root of y cubed, and we could take the cube root of y squared would be our leftovers. So leftovers over here, can't take the cube root of y squared. There are no restrictions in an odd root. Okay, and now all we do is evaluate this. Cube root of 27 is 3. Cube root of x to the 6 would be x squared. That's 6 divided by 3. Cube root of y cubed is just going to be y. And it leaves us with cube root of 2y squared. No restrictions. So we're kind of nitpicking this restriction business and the absolute values. Whenever I do my absolute values, I tend to be a little bit paranoid. And as you saw in AB, I put some in when I didn't need them. And then later on I thought, well, are some of these redundant? If so, I'll get rid of them. Okay, converting to entire radicals. Here's something to notice. 2 is the square root of 4, or the square root of 2 squared. 2 is the cube root of 8, or the cube root of 2 cubed. 2 is the fourth root of 2 to the 4th, and so on. So it follows that as long as this value is reasonable, then a is just the nth root of a to the n. Let's convert to an entire radical. We've got 5 root 3. I can rewrite 5 as the square root of 5 squared. Okay, now I've got only radicals I'm dealing with. So those are opposite operations, square rooting and squaring. Gives me root 25 times root 3, or root 75. And if you notice, that's the exact same question we started off with, just in reverse. This one over here, we've got cube root of 4xy. We're trying to make an entire radical here. So I'm going to cube root 2x. But to compensate, I'll also cube it. I'll write that a little more clearly. Cube root of 2x all cubed. Now, what does that give us? That's the cube root of 2 cubed is 8. X cubed is x cubed. By the cube root of 4xy. And now I just multiply what's under the root signs. So that'll be 32x to the 4 y. A classic non-calculator question is arranging from least to greatest. And that's going to involve us looking at these as entire radicals so that we can compare them. So 2 root 13, I really don't know how big it is. If I had my calculator, I'd just type it in and get a decimal approximation. So this is going to be the square root of 2 squared times root 13, or root 4 times root 13, or root 52. Okay, that's what that one is. Let's try my next one. I'm going to have the square root of 4 squared times root 5, or root 16 times root 5, or root 80. Oh, the red one's bigger than the blue one. I wonder where this one sits in all of this. It would be the square root of 5 squared times root 2, or root 25 times root 2, or root 50. Okay, now we can order them. This one is the smallest. This one is the middle because it's root 52. And this one is the biggest. So the order from least to greatest must be 5 root 2, then 2 root 13, and then 4 root 5. Okay. That's an analytical way to do it. On your calculator, we could have just done this. 2 square root of 13 is this much. Okay, it's about 7.2. 5 root 2, 7.07. Okay, that's smaller. And then finally, we could figure out 4 root 5. Ah, it's the biggest one. But it's kind of nice to do it analytically. Collecting like terms. If I have 3 root 2 minus 7 root 3 plus 4 root 2 plus 3 root 3, think of them as like terms. These root 2's, it's almost as if you're going 3x's plus 4x's. And these root 3's are like terms. They're like your y's. Okay. So if I were to do that with x's and y's, I'd say, all right, well, there's 7x's, and there's negative 4y's. Same thing over here. 3 root 2 plus 4 root 2 makes 7 root 2. Negative 7 root 3 plus 3 root 3 makes negative 4 root 3. I'll color code this. And again, you could test that by putting it in an original form in the calculator and then putting it in this simplified form. This would be another kind of classic question. If you want to simplify root 12 plus root 18 minus root 27 plus root 8. Well, first of all, each of these need to be put in mixed radical form. So root 12 is root 4 times root 3. This would be root 9 times root 2. Root 27 is root 9 times root 3. And root 8 is root 4 times root 2. Or 2 root 3 plus 3 root 2 minus 3 root 3 plus 2 root 2. Let's look at our like terms. In terms of root 2's, we have 5 root 2. In terms of our root 3's, we have 2 root 3 minus 3 root 3. So that's negative 1 root 3. Let's take a look at some of the rules for multiplying and dividing radicals. So here they are written formally. But I think the best way to think of this is when we multiply or divide, it's regular numbers by regular numbers. And we multiply our radicals, or what's under the roots, by each other. Radicals by radicals. And the index of the root must be the same. So you can't multiply a square root by a cube root. If we want to do that, we need to go back to grade 10 and look at exponential form. Okay, so let's suppose we've got this one. 9 root 2 times 4 root 7. I'm just going to go regular numbers times each other and roots times each other. 36 root 14. Again, I can check if this is true. So I'll go 9 square root of 2 times 4 square root of 7. Gives me 134.7. I wonder if that is 36 root 14. I hope so. Yes. Okay, we can do the same thing over here. We've got root 48 over root 6. We can divide these out. We can call this root 48 over 6. And 48 divided by 6 we know is 8. So this is root 8. But don't stop there. Root 8 can be split apart into the rootable of 4 and the leftover of 2, which gives us 2 root 2 in the end. Okay, so if you are able to divide evenly, you should. You can combine them. Similarly, if we've got root 2 over 9, the square root of the whole thing, we could convert that into root 2 over root 9. Or root 2 over 3. There's a square root we could actually evaluate there. And we really prefer our fractions like this. We like to have a rationalized denominator. We like to have a regular number in the bottom. The distributive property still holds. So in D, I'm going to multiply by this. So 3 times 2 makes 6. Root 2 times root 6 makes root 12. And I'm going to distribute my 3 root 2 by root 10. And that's going to give me 3 root 20. And I never give up an opportunity to simplify. So that's going to be 6. Square root of 12 is root 4 times root 3. 3 square root of 20 is root 4 times root 5. So this will be 6 times 2 times root 3 plus 3 times 2 times root 5. Or in the end, 12 root 3 plus 6 root 5. We can also distribute when we have binomials. So same thing is going to happen here. I'm going to multiply these together. That will give me 12 times the square root of 4. This will be negative 9 times the square root of 10. Okay, let's get another color on the go here. Plus 16 times the square root of 10. And finally, minus 12 times the square root of 25. Now some of these have perfect squares. In fact, maybe when you did that blue one, when you saw root 2 times root 2, you would realize that's just the number 2. But if you didn't, we can just work it out. Minus 9 root 10 plus 16 root 10 minus 12 times square root of 25, that's 5. Okay, so 24. Some like terms here. Negative 9 root 10s plus 16 root 10s make positive 7 root 10 minus 60. Or, when we're done, that's going to give us negative 36 plus 7 root 10. Again, you can check with your calculator. We'll do one last one in this video. So let's see what happens. I'm going to have binomials again. So 7 times 7, oh, very nice. Gives us a regular number, 49. And then I'm going to have negative 14 root 3. And then I'm going to have positive 14 root 3. And then I'm going to have minus 4 root 9. Or maybe I'll just call that 3. Root 3 times root 3 is going to be 3. Okay, now notice here we've got a negative 14 root 3 and a positive 14 root 3. They're going to be gone. So we'll just have 49 minus 12, or 37. Now if you take a close look at the original problem, you'll notice that these were the same thing, but one had a plus sign, one had a minus. Those are called conjugates. Same terms, but one has a plus, one has a minus. So they look like this. A plus B times A minus B. And they have a special property. They always multiply out so that their middles add to 0. So they always multiply just to a squared minus b squared. And we're going to make use of that property in the next video, but we should be aware of it. So on this one here, we might have been able to just use a shortcut and say, oh, I know that's going to be 49 minus 12. It'll be 37. Hope that you found this helpful, and we'll be back with the next part of Chapter 5. Hope that you'll tune in. Take care.